Right, children. Yes, any doubt from the previous class? If anyone wants to ask. No? Okay. We carry on with concentration terms. Last we did was molarity. Next, right on molality. Symbol small letter m. Right on. It is the number of moles of solute dissolved in 1 kilogram of the solvent. Dissolved in 1 kg of the solvent. Write on the formula. Formula is molality is equal to, if you remember last time I told you B stands for solute, so weight of solute divided by molecular weight of solute into 1000 divided by WA, means weight of the solvent. As usual, this is the number of moles of solute. And here you can label independent of temperature. Independent of temperature. That is, molality does not change with change in temperature. Now we'll be solving two numericals. As usual, I share on WhatsApp as well as chat box. Yes, the numerical is 0.4 mole of glucose is dissolved in water to prepare 272 grams of solution. Calculate molality of the solution. See, WB, weight of solute, will be 0.4 mole into molecular weight, 72 grams. So molality is number of moles of solute into 1000 divided by weight of solvent. Weight of solvent will be weight of solution 272 minus weight of solute. So this denominator is 200. So answer will be 2. We'll pronounce it 2 molal. We pronounce it 2 molal solution. I'm sharing second numerical. Yes, check your WhatsApp message or chat box. This is the second numerical which I've shared. An aqueous solution containing 24 grams NaOH by mass. Yes, one thing more to learn. If you remember, I taught you about 3 concentration terms involving weight by weight, percentage terms, weight by weight, volume by volume, and weight by volume. Remember, if nothing is specified, only we say like 20% solution, we always consider it weight by weight percent if nothing is specified, right? Okay. So this is an aqueous solution containing 24 grams of NaOH by mass. Density of the solution is 1.25 gram per cc. Calculate molarity and molality of the solution. Now see. Say solution is 100 grams. 24% NaOH. It means out of 100, 24 grams is NaOH and remaining 72 grams is water. and volume of the solution will be weight divided by density. So volume of solution will be
76 grams.
sorry.
That would be 76 grams, right? Of H2O.
This
No, yes, sir,
So
for
it should
H2O.
be 76 gram H2O.
sorry 76. Oh, 76 grams. You're right. So divided by density, this will come out to 80 cc. Cc or milliliter is one the same thing. Now we have to calculate molarity and molality. Molarity, solute 24 grams divided by molecular weight into 1000 divided by volume of solution is 80. This will be 7.5 molar. 7.5 molar. This is one answer. Second, molality. Again, weight of solute 24 divided by molecular weight into 1000. This much is common. Now here we use weight of solvent. Weight of solvent is 76. This will come out to 7.89. We pronounce it molal. So 7.89 molal solution. I hope you have noted down. Now we start with the next concentration term. Write down parts per million. Parts per million. PPM. PPM. Write down this concentration term. This concentration term is used for extremely dilute solutions. Extremely dilute solutions. It is defined as the number of parts by weight or by volume present in 1 million parts of the solution. 1 million parts of the solution. Now, write down the formula. This ppm will always be for the solute, right? So ppm will be equal to weight of solute, or we can use volume of solute divided by weight of solution or volume of solution. Numerator and denominator, either both should be masses or both should be volumes, and their units should be same. Multiplied by 1 million, 10⁶. Now for this, I'm sharing one numerical. Yes. Numerical is 50 liters of air contains 2 cc of sulfur dioxide as sulfur dioxide in it. Calculate the concentration of SO2 in air in ppm. I hope you know sulfur dioxide is present as a pollutant in air. So we represent the concentration of pollutants in terms of ppm only. So ppm of SO2 will be volume of SO2, it's given 2 cc divided by volume of solution. Air is solution. It is 50 liters. 50 liters will be, unit should be same. So 50,000 cc multiplied by 1 million. it will be 40 ppm. So we can say 40 liters of SO2 is present in 1 million liters of air, or so many cc present in 1 million cc of air. Unit should be same. Remember that. Next concentration term, and this will be second last concentration term, normality. Normality. Within bracket, symbol is capital letter N. Normality N. It is the number of gram equivalents of solute present in 1 liter of the solution. Present in 1 liter of the solution. Now, in this case, before I give you the formula for calculating normality, I'll give you some additional information. Number of moles is weight divided by molecular weight. We divide the given mass by molecular weight of the substance, we get number of moles. Similarly, if we want to convert given mass into number of gram equivalents, we divide the given mass by equivalent weight of the substance. In CBSE, you will not study equivalent weight anywhere. Neither it was there in 11th standard, not in 12th standard. I'm talking about CBSE. But normality will be frequently used in CBSE calculations as well as JEE mains. Now for that, I'm giving you some additional information. Note down everything and enclose this additional information in a box later on. Number of gram equivalents is equal to weight divided by equivalent weight. Now the problem is, what is equivalent weight? Equivalent weight is equal to molecular weight divided by N factor. Now what is this N factor? Write down separately. N factor may be total positive or total negative charge on cations or anions of the salt, or acidity of the base, or basicity of the acid, or number of electrons transferred during a reaction. So I gave you different ways in which we can think of N factor of the substance. And I'll give you an example of each and every case. For example,
Sir, last one, can you please repeat?
okay, last one was number of electrons transferred. Now, I'm giving examples. Equivalent weight of sulfuric acid will be molecular weight divided by 2. I hope you know acids have basicity and bases have acidity. Those who don't know, let me tell you. What is basicity of the acid? Number of H+ ions produced by one molecule of the acid is its basicity. Similarly, acidity of the base is number of hydroxide ions produced by one molecule of the base. Right? This is acidity, basicity. Sulfuric acid is dibasic because one molecule will produce 2 H+ ions. So molecular weight 98 divided by 2. 49 is the equivalent weight. Let us say HCl 36.5 N factor is 1. Sodium carbonate. Molecular weight is 106. Can anyone tell me what is the N factor? Yes, try. Let it be wrong. What is the N factor?
2.
2. See, if you think of ions of sodium carbonate, one molecule will give 2 sodium ions and 1 carbonate ion. You take positive charge on cations or you take negative charge on anions formed. Either of the two, value will be same. Total positive charge is 2 units, or you can consider total negative charge, a charge on anions, that is again -2. So value is 2. It means N factor is 2. So in this case, equivalent weight will be 53. H₃PO4, phosphoric acid, N factor is 3. So divided by 3. H₃PO3, I don't remember that molecular weight. Let us say molecular weight is X. Now this is the acid which has 3 hydrogen atoms, but on ionization this will release only 2 hydrogen atoms as H+ ion. So according to the formula, it appears to be tribasic, but it is not. It is a dibasic acid. So equivalent weight will be divided by 2. More examples. So I've taken examples of based on charge of cation, charge of anion, acidity, basicity. Now I'll take example based on number of electrons transferred. KMnO₄ in acidic medium. In 12th standard, you will be performing redox titrations in the lab. Oxalic acid versus KMnO₄ or more salt versus KMnO₄ in the presence of acid. Molecular weight of KMnO₄ is 158. When we use KMnO₄ in acidic medium, there is a transfer of 5 electrons. So divided by 5, this is the equivalent weight of KMnO₄ in acidic medium. But when we use KMnO₄ in basic medium, number of electrons transferred is 3. So KMnO₄ in basic medium, 158 divided by 3. This is the equivalent weight. Right? So that's what is N factor, and how do we use N factor to calculate equivalent weight of the substance? It means one thing is clear: same substance can have different values of equivalent weight in different reactions, right? Whereas molecular weight does not change. Now I'm giving you the formula for normality. Normality is equal to weight of solute divided by equivalent weight of solute multiplied by 1000 divided by volume of solution, which should be in milliliters, that is cubic centimeters. I'll modify this formula. Weight of solute into 1000 divided by volume of solution equivalent weight. If you remember, I told you equivalent weight is molecular weight divided by N factor. So denominator will be molecular weight and N factor will be numerator. Molecular weight, and this is N factor. Look at this part. What is this? This is, anyone? This is molarity. So I can say this is molarity into N factor. So best is first you calculate molarity, multiply by n factor, that will be the normality. I'll give you a verbal example. Like if you consider 1.2 molar sulfuric acid, 1.2 molar sulfuric acid, its normality will be, yes,
2.4.
normality will be
2.4.
2.4 because n factor is 2. Right. One numerical. Check your WhatsApp message. Yes. Numerical is 21.2 grams of sodium carbonate is dissolved in water to prepare 400 cc solution. Calculate normality of the solution. Very simple numerical. Normality will be weight of solute divided by molecular weight into 1000 divided by volume of solution 400. This is molarity. Molarity multiplied by n factor. N factor of sodium carbonate is 2. So this answer will come out to 1. We'll pronounce it 1 normal. Right? 1 molal, 1 molar, 1 normal. That's how we pronounce. Now, coming to the last concentration term. I hope you have noted down. Last is strength. Or you can write strength per liter. If you remember in class 11 titration, after calculation, you represent strength of the solution in grams per liter. And if you remember there in 11th standard, you might have used the formula strength is equal to normality into equivalent weight. In 12th standard, again, you'll be calculating strength of the solution in redox titrations. But in 12th standard, you'll be using the formula strength is equal to molarity into molecular weight. So these are two formulas which I'll give you after the definition. Pattern. It is defined as the number of grams of solute present in 1 liter of the solution. Present in 1 liter of the solution. Write down the formula. Strength per liter is equal to normality into equivalent weight of solute, or we can say molarity into molecular weight of solute. Concentration term itself gives you units. Strength per liter will be grams per liter. Right? Now, in this case, I'll share one numerical which will solve by two different methods. On WhatsApp, it has been shared 2 times. Please be careful. It has been shared 2 times. Right. Hmm. 8 grams of ethanol, molecular weight is 46 and density is also given, is dissolved in 5 moles of water. Calculate strength of the solution. See, water is equal to 5 moles will be 90 grams of water. And since density of water is 1 gram per cc, we can say 90 grams of water is 90 cc of water. We are given 8 grams of ethanol and the density of ethanol is 0.8 gram per cc. It means 8 divided by 0.8, it is 10 cc ethanol. If we add these two volumes, that will give the volume of solution. So volume of solution, 90 plus 10, 100 cc. Now, after this, we'll be using two methods. First method is we'll calculate molarity and then multiply by molecular weight. So molarity will be weight of solute 8 grams divided by molecular weight into 1000 divided by volume of solution is 100. This will come out to 80 divided by 46. This is the molarity. Multiply this molarity by molecular weight of ethanol, that will give strength of the solution. So strength per liter 80 divided by 46 into molecular weight 46. 80 grams per liter. This is the answer. Be a little fast in noting down. Now, second method is a unitary method. Very, very simple unitary method. Hundred cc solution contains ethanol equal to 8 grams. In 100 cc solution, ethanol present is 8 grams. And by definition, amount of solute present in 1 liter of the solution, that is strength of the solution. 1 liter will be 1000 cc. So 1000 cc solution contains 8 divided by 100 into 1000, 80 grams per liter. So you can use either of these two methods. But in 12th standard, you'll be using molarity into molecular weight when you're performing redox titrations. So we have finished all the concentration terms. Now we are going starting with an absolutely new topic. Right now, solubility. Solubility. It is defined as the number of grams of solute, which can be dissolved in a specified amount of solvent to prepare a saturated solution, at a particular temperature. See, in the definition you have written number of grams of solute which can be dissolved in a specified amount of solvent. Generally, this is, I'm saying generally, right? Generally, this specified amount of solvent is taken as 100 grams of solvent, right? In most of the cases. Continue. It depends on many factors like nature of solute, nature of solvent, temperature, pressure, etc. Temperature, pressure, etc. And one thing more, when you're writing notes, for temperature, write T, for pressure, write on P so that you can save time. Now, in the next paragraph, when you're writing, you'll not be able to understand anything. You just keep on writing, keep on writing. Once I've finished dictating, then I'll explain what's the meaning of this paragraph. Right on. Next paragraph. Solubility depends on forces of attraction between molecules of different components and forces of attraction between molecules of the same component. So just keep on writing, don't try to understand. I'll explain later on. Full stop. If EAA, right, like this, if EAA and EBB are the interaction energies in pure A and pure B respectively, and EAB is the interaction energy between molecules of different components, then the extent of solubility depends on the value of following expression. Write down this expression. Expression is twice EAB minus EAA plus EBB. I'm sure you're not able to understand anything, and just don't worry. Just one more sentence, after that I'll explain. Higher the value of this expression, more is the solubility. Now you can relax for a while. You need not write anything. Just concentrate what I'm going to explain about this paragraph. See, if you remember in 11th standard, you might have studied lesser the energy, more the stability. It means every system has the tendency that its energy should be minimum so that its stability is maximum. That's what we discuss in thermodynamics as well as in chemical bonding in 11th standard. On this basis, we can say all those processes which are exothermic, means reactions or physical processes which proceed with loss of energy, they should be spontaneous, because loss of energy means energy left with the system will decrease and stability will increase. Why is a bond between two atoms formed? The reason is bond formation is an exothermic process. When bond is formed, energy is released. Energy is released means energy of the molecule formed will be less than the total energy of combining atoms. How much energy is released during formation of a bond? That will depend on strength of the bond. It means if the bond is strong, more amount of energy will be released. If weak bond is formed, less amount of energy will be released. Similarly, reverse of this. If you want to break a bond, will have to supply energy. It means breaking a bond is an endothermic process. And in this case also, if a weak bond is to be broken, we have to supply less amount of energy. If a strong bond is to be broken, we have to supply more amount of energy. Remember, any attraction between two particles, even if it is not a chemical bond, any attraction between two particles is like a chemical bond only. So attraction between particles will be exothermic process. Now I'm coming to EAA, EBB, and EAB. If we have pure component, pure compound A in one beaker, pure compound B in another beaker. In one beaker, I have molecules of A and A and A only. Attractions between these particles will be called EAA, will be called AA attractions. Attraction between A and neighboring A will be called AA attraction. How much energy is released during formation of this attraction, or how much energy is required to break this attraction? That is EAA. I called it interaction energy of A. Similarly, in pure compound B, there will be attractions between particles of B and B, which will be called BB attraction. Energy required to break this attraction or energy released during formation of this attraction will be called EBB. Now, when we mix these two components which were taken in two different beakers, when we mix them to prepare a solution, look here. B will come in between A and A. A will come in between B and B. It means when B comes in between A and A, AA attraction will be broken. And to break this attraction, how much energy is required? EAA energy will be required. It means this will be an endothermic process. Similarly, when A comes in between B and B, this attraction will be broken and energy required to break attraction between B and B will be EBB. So this is also an endothermic process. So when we mix A and B to prepare a solution, total amount of energy which is required to break attractions will be EAA plus EBB. Now, after breaking attraction, 2A and A are separated from each other, 2B and B are separated from each other, and when they come in contact with each other, new attraction between A and B, new attraction between A and B will be formed. So two attractions between AB and AB will be formed. During formation of AB attraction, energy release will be EAB. And since two of this type of attractions are formed, total energy release will be twice EAB. This is exothermic process. Now, if this exo process, that is, if energy released is more than the energy consumed, then overall process will be exothermic. I hope it is clear. I'll repeat. If energy released during formation of these attractions is more, energy required to break these attractions is less, overall process will be exothermic, that is, energy will be released. If energy is released, then process will be spontaneous because stability will be attained. And the last sentence says, higher the value of this expression, more is the solubility. Means what? If the value of this expression is high, it means more amount of energy is released. More energy is released means less energy is left. It means more stability will be attained. That is why solubility will be high. I hope that's clear. Any doubt, anyone?
No one. No, sir.
Okay.
No,
But still, if you feel you want to ask, you can call again. You can call tomorrow. Don't hesitate. I'll explain again. Now we'll consider solubility of solid in liquids and solubility of gases in liquids. Today we are going to finish solubility of solids in liquids. So write on A part. A part. Solubility of a solid in a liquid. Solubility of a solid in a liquid. I'll give a very simple example. Tell me which term would you like to use for it. You know, ionic compounds are soluble in water, like sodium chloride is soluble in water. But ionic compounds are not soluble in organic solvents, like NaCl is not soluble in benzene. But if we consider organic compounds, covalent compounds, like if we consider wax, wax is soluble in benzene, but it is insoluble in water. What is the term? I know you are aware of it. What is the term used for it?
Immiscible.
No, we say this dissolves in this. It's pretty special, simple si term. Okay.
Soluble and insoluble.
Chali. When I dictate you, maybe you'll be able to tell. Pattern. Every solid solute does not dissolve in every liquid solvent. Does not dissolve in every liquid solvent. For example, sodium chloride dissolves in water, but not in benzene. Whereas wax, candle, right? Wax dissolves in benzene, but not in water. Also, generally polar and ionic compounds dissolve in polar solvents and covalent or non-polar solvents, non-polar solutes dissolve in non-polar solvents. Now tell me, what is the term used?
Well, polarity.
Like dissolves like.
Yes, madam, that is like dissolves like. So when we say like dissolves like, it means polar compounds or ionic compounds, they are soluble in polar solvents. Non-polar compounds are soluble in non-polar solvents. Although exceptions are there are many exceptions, like glucose is a covalent compound, but it is very much soluble in water. Exceptions are there. Next paragraph. Now, this I'll explain and then dictate. Look here, let us say this is a beaker. I take some water and add some sodium chloride to it or any other solute. I stir, it goes into solution. I add more solute, stir, it goes into solution. And ultimately we get a saturated solution. That is something very simple. Now, think on molecular level. When solute dissolves, that solute, those particles of solute which have already gone into solution, they are in a state of motion. They are moving. When they move, they strike the surface of undissolved solute particles. I'll repeat. Those solute particles which have gone into solution, they strike the surface of undissolved solute particles, and sometimes they stick to the surface of undissolved solute and they remain in the solid form. This process is called crystallization. So one process is solute is going into solution, that is dissolution. Second process is opposite, that is some solute particles, they stick to the surface of undissolved solute and crystallization takes place. In the beginning, dissolution is fast, crystallization is slow. But as the time passes, as we dissolve more and more quantity of solute, dissolution slows down and crystallization speeds up. And as you studied in 11th standard in equilibrium, what happens? Ultimately, number of particles of solute which go into solution becomes equal to number of particles which crystallize out. That is, a state of equilibrium is attained. And at this equilibrium, saturated solution is obtained. And this equilibrium will be used in Le-Chatelier's principle in today's topic. All right, now. Right in the next paragraph. During dissolution, concentration of solute in the solution, increases. Some dissolved solute particles collide with the surface of undissolved solute particles and stick to their surface, which leads to crystallization. When the number of solute particles going into solution becomes equal to the number of solute particles which crystallize out a state of equilibrium is attained and the solution becomes saturated. This equilibrium is represented as follows. So solute which is in the solid state will be in equilibrium with solute which is present in the solution, right? They are in equilibrium with each other. And when this equilibrium is attained, solution has become saturated. Now this equilibrium will be used in further topic today. Now there'll be two parts of this topic. Number one, effect of temperature on solubility of a solid in a liquid. Effect of temperature on solubility of a solid in a liquid. And this can be explained on the basis of Le-Chatelier's principle. if dissolution is exothermic, then increase in temperature now this I'll complete later. Now tell me, if we dissolve a solute in solvent, solid solute in solvent, imagine the process is exothermic, and if we increase temperature, then let us say I'm writing heat here. If we increase temperature, in which direction will the equilibrium shift?
Backward.
Yes, it will shift in the backward direction. Okay. If anyone has confusion, please ask me. I know some children have confusion. Doesn't matter. I'll explain. This is something which is based on class 11 equilibrium Le-Chatelier's principle. See, whenever you want to apply Le-Chatelier's principle, you have to think very carefully. If we change temperature, if we change pressure, if we change concentration, the change which is done on the state of equilibrium is called stress. Like if I increase temperature, increasing the temperature is a stress. If I decrease the temperature, decreasing the temperature will be called stress. So when equilibrium is subjected to a stress, then what will happen? This equilibrium will shift either in the forward direction or in the backward direction. Now, how do we decide in which direction will the equilibrium shift? Very simple. Whatever stress, whatever change we impose, opposite of that will take place. Means what? Means what? Like in this case, when we increase temperature, now what is the opposite of increase in temperature? Temperature should decrease. I'll repeat. If it may be confusing for a couple of students, when we increase temperature, effect will be that the temperature should somehow decrease. Temperature will decrease in an endothermic process. This process is exothermic, means forward process is exothermic, whereas backward process is endothermic. So when I increase temperature, temperature should decrease, and temperature will decrease in the backward direction. It means equilibrium will shift in the backward direction. And if equilibrium shifts in the backward direction, it means solute which is present in the solution will change into solid form. When solute changes into solid form, it means crystallization takes place, or we can say solubility decreases. Right? Similarly, if you apply decrease in temperature, discussion will become opposite. Okay, we'll complete the sentence. I forgot what did I dictate. Maybe I'll repeat. Could you please tell me the sentence?
If dissolution is exothermic, then increase in temperature.
Increase in temperature shifts the above equilibrium towards LHS, left hand side, so that the solubility decreases. Solubility decreases. So never have the feeling that whenever we increase the temperature, solubility in any case has to increase. No, whether the solubility will increase or decrease will depend on whether the process is exothermic or endothermic. Now in this case, write down one example. For example, NaOH in water. NaOH in water. When we dissolve sodium chloride in water, it becomes so hot that you can't even touch the beaker. If you want, you can ask your lab assistant to show you. He'll dissolve some sodium hydroxide in water, try to touch the beaker or test tube. It becomes very hot, process is highly exothermic. It means solubility of sodium hydroxide in water will decrease with increase in temperature. If I want to increase solubility of NaOH in water, I'll have to cool the solution. Temperature has to be decreased. Next paragraph. Now the opposite. On the other hand, if dissolution is endothermic, increase in temperature shifts the above equilibrium towards right hand side so that the solubility increases. For example, ammonium chloride in water, NH4Cl in water. If you remember, in class 11, while performing salt analysis, in third group analysis, you add ammonium chloride followed by ammonium hydroxide. When ammonium chloride is added in group 3 analysis, touch the test tube, you'll have the feeling it becomes cold. The process is endothermic. Second part, effect of pressure on solubility of a solid in a liquid. Solubility of a solid in a liquid. I think you know about it, but still I'm sure you'll give a wrong answer. If we dissolve solid in a liquid, how do we decide in which direction will the equilibrium shift? If we increase pressure,
Sir, in the side where there are fewer number of moles of a gas.
Number of
Yes.
gaseous moles.
Yes, gaseous moles. You very rightly said gaseous moles. If we increase pressure, equilibrium shifts in that direction in which number of gaseous moles is left, but gaseous moles is less. But in the present topic, we are not talking about any gas. We are dissolving a solid in a liquid, no gases involved. It means in this case, when we increase or when we decrease the pressure, there's no effect on solubility, right? The reason is when we change the pressure, volume of the solid or volume of the liquid changes negligibly, or we can say there's no change in volume on changing the pressure. Therefore, there's no effect on solubility of a solid in a liquid. So just one sentence you have to write down. Pressure has no effect on solubility of a solid in a liquid because both the components are incompressible. Means we cannot compress them, are incompressible. That is, change in pressure does not change their volume. That was the only written part for today. Just I'll take 2 minutes. Next time we are starting with solubility of a gas in a liquid. Do you remember there was a topic in 11th standard? I'll pretend that I've forgotten which chapter it was, where we talked about solubility of a gas in a liquid, and there was some law. We defined the law in 11th standard. Okay, I'll give you the hint. It was in equilibrium. Solubility of a gas in a liquid based on some law. Do you remember Henry's law? Okay. So this will be a very important topic next time. Henry's law. In 11th standard, there was no numerical based on Henry's law, but it will be mathematical in 12th standard. Very, very important topic. See, if we take a liquid in a cylinder and it is fitted with a piston, and there's a gas above the liquid, molecules of the gas will be in a constant state of motion. And when these gaseous molecules strike the surface of liquid, due to moment of inertia, some gaseous particles, they go deep into liquid solvent. And when they go deep into liquid solvent, they dissolve. It means I can say more the number of gaseous particles which strike the surface of liquid, more will be the solubility. When will the number of gaseous particles on the surface of a liquid be high? When the pressure of the gas is high or low?
High.
High. So if pressure of the gas held above the liquid is high, number of gaseous particles which strike surface of the liquid will be more. It means the solubility of the gas will be high. That's what is Henry's law. If you remember, in 11th standard, we defined it that solubility of a gas in a liquid solvent is directly proportional to pressure of the gas above the liquid solvent. But this will take mathematical shape in 12th standard. That will take up next time. Right? Right, Chala. Anything you want to ask, or you can log out?
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye.
Thank you,
Thank you,
sir.
sir. Bye, sir.
Sir, by what time will you be free tomorrow?
You call me anytime. If I do not pick up your call, I'll call back whenever I'm free.
Okay, sir. Thank you.
कभी hesitate मत करो, anytime.
जी, sir.